All right. So now we are ready to study the important theorems that are present, in terms of the properties of the discrete time Fourier transform. So let us take a few minutes to quickly study these properties. They are somewhat easy, but having studied already the discrete time, the properties of the discrete time systems and sequences, these are we use those principles to come. The first one is the principle of linearity. Okay, what does linearity say? That so I will just write down the corresponding property here. We will. Okay, linearity says that if I have two sequences x of n with a discrete time Fourier transform x e of j omega and y of n with a discrete time Fourier transform y e of j omega, then a times x of n plus b times y of n. Okay, what will it be? Its Fourier transform. This will be summation n equal to minus infinity to infinity a times x of n plus b times y of n. This is my input. This is my input sequence e power minus j omega n. Just expand it and you can write it down that this is equal to a times x e of j omega just by expanding the summation, and the second term will be b times y e of j omega. Okay, superposition, scaling, both satisfied, that gives you linearity. This is an inherent property of the discrete time Fourier transform. Why is it useful? You can add sequences and you can get their combined Fourier transform just by adding their individual Fourier transforms. So again, a very useful property that we will use again and again in our study, and it is a useful property. So this is property number 1 or theorem number 1. Second, theorem number 2 is a shift property. Basically, this is a time shift. Now, if you have a sequence x1 of n which is equal to x of n minus n naught, a time shifted sequence. Okay, and how would you define this? If n naught is greater than 0, it would be a sequence that is delayed in time. This is delayed. So basically it would have shifted to the right. This particular sequence would have shifted to the right. On the other hand, if n naught less than 0, you will have an advance operation. Basically the sequence will move to the left with respect to the origin. So basically it will occur earlier in time. So the important thing to note is any shift, whether it is a advance operation or a delay operation, let us say that we are interested to know that, then the corresponding discrete time Fourier transform x1 e of j omega is equal to summation n equal to minus infinity to infinity x1 of n e power minus j omega n. Substitute for x1 of n. This is summation n equal to minus infinity to infinity x of n minus n naught e power minus j omega n. Okay. Do the replacement, m is equal to n minus n naught. So the summation will be m equal to minus infinity to infinity x of, now within brackets you have m, n minus n naught equal to m, and e power minus j omega, this will be equal to m plus n naught, basically replacing for n. Okay, so this can be written as e power minus j omega n naught summation m equal to minus infinity to infinity x of m e power minus j omega m, and this is nothing but x e of j omega. So if you have a shift in the time domain, the corresponding expression is e power minus j omega n naught x e of j omega. Okay, that is what is given as the theorem which relates to shift. So if you have x of n minus nd, nd is any integer, what you will get is e power minus j omega nd. That will be a phase term, and the original expression e power minus j omega. Now, if you were to look at the magnitude response, magnitude of e power minus j omega nd x e of j omega, the magnitude of e power minus j omega nd is equal to 1. So, this is equal to x e of j omega. Now, this is a very useful result. What it says is, if you delay a signal in time, it will not affect the magnitude response. The magnitude response will be exactly the same. Will it affect the phase response? Yes, it will affect, because you have e power minus j omega nd, but it will not affect. So, a shift in time shift, okay, does not affect the magnitude response. Does not affect the magnitude response. Again, useful result that you can keep in mind and apply it in whenever there is a need for that. Okay, a third one. Now, of course, just like you can do a time shift, you can also do a frequency shift. Let me just you can refer back to the previous page or refer to table number 2 in the book. Let's just look at the other properties. So, this is property number 3 or theorem number 3, which is called frequency shifting. Okay, how do you shift in frequency? Now, give me an example of where we would shift in frequency. You know, when we want to receive a radio signal, we will receive it at some carrier frequency. We want to shift the frequency from the carrier frequency down to baseband, omega equal to 0. That is an operation where we know we need to do frequency shifting. So, like that, there are many applications where we would like to do conversion of frequency from high frequency to low frequency or low frequency to high frequency. Again, this is a very important aspect. Now, we would like to see how this happens and how to interpret. So, if you have x e of j omega given by summation n equal to minus infinity to infinity x of n e power minus j omega n, and you want to look at what is the effect of shifting by omega naught, e power x e of j omega minus omega naught. Okay, so if you have changed omega to omega minus omega naught, you have to change it on the right side also, n equal to minus infinity to infinity, x of n e power minus j omega minus omega naught times n. Wherever there is omega, you have replaced it with omega minus omega naught. Okay, let's simplify this. This is summation n equal to minus infinity to infinity x of n. I am going to simplify this expression, e power j omega naught n e power minus j omega naught n, j omega n, right. And if I combine these two terms and treat it as some x1 of n, then x1 of n has got a discrete time Fourier transform which is given by x e of j omega minus omega naught. And what is x1 of n? x1 of n is nothing but e power j omega naught n times x1 of n. Okay. So, if x of n, sorry. Yes, thank you. So, this is what shifts the frequency by omega naught. So, you take the sequence multiplied by e power j omega naught n, that will shift the sequence to a center frequency of omega naught. Now, what is the shifting by omega naught? So, supposing you have a spectrum that looks like this, if this was x e of j omega, x1 x of n with the magnitude or the discrete time Fourier transform x e of j omega, then x1 of n which is equal to e power j omega naught n times x of n. That will be the corresponding spectrum, will be the same spectrum but shifted to omega naught. Okay, this is x1 e of j, or maybe write it as x of e of j omega minus omega naught magnitude. Okay, so the spectrum gets shifted over by omega naught. As I mentioned to you, this is a very useful, very powerful result. Let me just explain it in terms of an application. Okay, an application that we will encounter in communications whenever we want to do wireless communications or radio communications, we do that. So we do a operation called modulation, x of n cosine omega naught n. Okay, that is what we do. Multiply the information bearing signal with a carrier signal, and we call that as cosine omega naught n. So if you write this down, this is x of n. Cosine omega naught n can be written as 1/2 of e power j omega naught n plus e power minus j omega naught n. So you can think of it as two terms, half x of n e power j omega naught n plus half x of n e power minus j omega naught n. Okay. Remember the property of linearity. If you want the spectrum of xn e of j omega n, you can take the spectrum of these two terms and add them together. So the first term, we'll call it the first term and the second term. So x of e of j omega is given here. This is x e of j omega. Now x1 is multiplied by e power j omega naught n, so it is shifted to the right by omega naught. Okay, this is omega naught, this is the first term, the spectrum of the first term. The second term is on the other side, and each of them has got a height equal to 1/2 if the original one has got a height of 1. So the green also has got a height of 1/2. Remember the scale factor. So this is the second term. So what does modulation mean? What does the frequency shifting do? When you multiply the sequence with an exponential, complex exponential, e power j omega naught n, the spectrum moves to the location of omega naught, and this is a very useful, very powerful result that we will use time and again. So let's go back to the table that we have obtained. So we can tick off this expression also. Okay. Now this time reversal is actually a very simple result. Let me just do that for you. It's a simple substitution. So again, fairly straightforward. Let's look at that. Okay. X e of j omega is equal to summation n equal to minus infinity to infinity x of n e power minus j omega n. Okay. Now, if you replace n with first, let us say that you do this expression x e of minus j omega. This will be summation n equal to minus infinity to infinity x of n e power j omega n, and then you replace m with minus m equal to minus infinity to infinity x of minus m e power minus j omega m. Okay. So we get the result that x of minus m, time reverse sequence, is the corresponding expression for the discrete time Fourier transform is a time reversal in terms of frequency, x of e of minus j omega. Now, if x of n, so basically this is one result that you can tick off. So x of minus n is x of minus j omega. Now if it so happens that x of n is real, then you have the following additional property. Okay, if x of n is real, if x of n is real, then we know that the following result is true: x conjugate of n is equal to x of n. Okay, so in that case, look at x e of j omega conjugate. This will be equal to summation n equal to minus infinity to infinity x conjugate of n e power j omega n. Both terms are conjugated, but x conjugate of n is the same as x of n because x of n is real. So then what you get is n equal to minus infinity to infinity x of n e power j omega n, and replacing m with minus m, we get m equal to minus infinity to infinity x of minus m e power minus j omega m, and this gives us a second expression for the discrete time Fourier transform of x of minus n. X of minus n has got a discrete time Fourier transform equal to x conjugate e of j omega. Okay, so basically time reversal can produce two results. If for any general sequence it is e power x e minus j omega. If it is a real valued sequence, then you can just take x of e of j omega and take a conjugate, and you will get the result. So that confirms the property of x of n.